Hey everybody, welcome back. Alrighty, so this will start the actual lectures per se, where we start going through content. Welcome, first of all, back. And so what we're going to do today is talk about psychology, science, and math. What the heck? Yeah. Some of the psychology textbooks I've used in the past have had a richer section on the history of psychology, talked about some of the figures and their influence, and I actually, in fact, teach the C85 History of Psychology course here now and then. And I actually think some of these historical stories are really important to understanding the psychology we have today. And so what I'm going to do in the next couple lectures is weave in some of that content that isn't in the textbook, but that I think is really important to get a good understanding. And so you're especially going to see that in this chapter in the next few lectures. And yeah, it will start here with psychology, science, and math. So I want to kind of throw this question out there. Can psychology be a science? Well, of course, at UTSC, we say psychology is a science. We give you a bachelor's of science if you get a psychology degree. And absolutely, there certainly is a lot of psychological research now is validly scientific research. And you'll find out as we go through this chapter, and especially the next one, chapter 2, what that really means. What does it mean to be a science? But I'm kind of throwing this out here from a more historical perspective. Imagine this in the pre-psychology days. One of the things you'll learn about is psychology is not that old. 130 years, 140 years, something like that, 150 years tops. Before that, before the late 1800s, there was no psychology. There was a physics, there was a chemistry, there was a biology, all those other sciences, but there was not a psychology. And there was really a question in people's mind, can psychology be a science? Could it ever grow into a science? And there were skeptics. There were a lot of people that said, no, it cannot reach that. And that is in part because of the next line I have here, the importance of math to science. The scientific community had witnessed the use of mathematics. We're going to talk about that a little bit today and how important it was, and had started to really identify math and science. And so now if you want to be a science, you have to kind of connect with mathematics in some way. And some of the early research that led to the birth of psychology was exactly that. People showing that you could understand the mind with numbers. Okay, so I want to walk you through a little bit of that. I would like to start with Pythagoras. So Pythagoras, by the way, is one of my own personal heroes. There's not that much known about him. He's a very mysterious kind of figure. He's sometimes kind of related more to a cult leader of a sort because he had followers in a very strict sense. People who sort of followed Pythagoras. This is before Twitter. They actually probably followed him physically around, listened to him, talked to him, and largely followed his teachings, and they were wide-reaching. As one example that I personally associate, Pythagoras was an early example of a vegetarian, and he insisted that all of his followers also be vegetarians. He considered it the only sort of ethical place to be. As a rational thinker, he thought every rational thinker should naturally come to the conclusion that a vegetarian lifestyle is the right one. I am a vegetarian as well. I'm a vegan wannabe. So you're going to kind of get some of that throughout the course. I can't help but be who I am. So you're going to hear some of that. But that always made me interested in Pythagoras. But that's not really what we're going to focus on today, but rather Pythagoras's connection to mathematics. Pythagoras really started to believe that everything in reality followed mathematical relationships. And that when you understood the mathematical relationships, you understood the phenomenon. So let me give you one extreme example of this, mathematics and music. Let me just click on this for a second here, which should have launched. Skip verification. Sure, there we go. Video unavailable. So math and music. Let's just find something else then. Fine, you want to be okay. Unless there's a relatively short one. Yeah, these are all 13 minutes or more, and I don't want my whole lecture to be too much more than that. So let me just say, the fact that you can see all of this suggests that there is a strong connection between mathematics and music. And I'm going to let you kind of mine some of these on your own. So just know they're out there and check them out. Let me give you just a very simple example, and that is something like guitar strings, okay? Pythagoras was one of the first to say that, hey, the length of a vibrating string determines how it sounds to us. And in fact, certain sounds, when you combine them together, sound pleasant to us. And the ones that sound pleasant tend to follow very clear mathematical relations. There is an underlying mathematics to beautiful music. And that just, when you just kind of think about that, beautiful music. Well, beautiful music is what we call an aesthetic judgment. That beauty is in the eye of the beholder, right? But we can say that certain kinds of music most people find pleasant, and there are other kinds of music they find unpleasant or jarring. The unpleasant music tends to fly in the face of these mathematical relationships. The pleasant music tends to follow them. So math can predict a psychological reaction to the stimulus, whether somebody likes it or doesn't like it, which is kind of cool. Now, of course, you know that he also played a lot with geometry. You guys know Pythagoras' theorem. So he said, anytime you see a right angle, so just kind of imagine this. We kind of grew up with Pythagoras' theorem, right? But this dude's walking around and he's seeing like a wall in a room that's got a right angle. And he's saying at some point, well, I wonder what the distance is between the tips of those lines that make up the right angle. And I don't know why, but he started measuring things, and he came up with this realization that when you have a right angle triangle, if you square that value and you square that value, it will equal the c squared. And that this is a relationship that always holds up every time you have a right angle here. And so again, another example there, we often build buildings with right angles, right? And another example of how there's some mathematics that sort of underlies it all. That's very cool. And so Pythagoras was big on that underlying mathematics and talking about it. But again, what I really want to stress about Pythagoras and what he was saying is this view that he held, that there is an order to things in the universe. Things are not just randomly out there. There is an order, and that order can be captured by numbers. So when you capture something with math, that implies you really understand it. The goal of science is to understand our world better. And so therefore, the notion is now we're getting that connection of math with science. Well, how do you know you understand? Well, because you can capture what you're studying mathematically. Okay. Now, this was further strengthened, of course, by Isaac Newton. Isaac Newton, look at the dates there, 1600s to 1700s. This is 150 years. He died 150 years before psychology was born. Okay. Several generations before psychology was born. He was a physicist, of course, amongst other things. Everybody was a lot of things in Newton days, whatever you want to call them, mathematicians, all sorts of things. But what Isaac did that was really interesting, and we can see it in his second law of physics here, is he started to capture the behavior of objects in the world using mathematical formulas. So things like if the force acting on an object equals its mass times an acceleration. So that you can actually calculate things like forces based on something's mass and how fast it's moving. And so he started coming up with a number of these formulas to describe bodies in motion and what affected them. And this really impressed people. The fact that you could actually see a little ball rolling down a hill and go, oh yeah, that's kind of interesting. It's getting faster and faster and faster. And he said, well, yeah, it is, but it's getting faster and faster and faster according to a very specific formula. And now you're starting to say, oh, wow, you're really getting a deep understanding of what's going on. So, the book that he wrote, the Principia, again, this is about 200 years before psychology. It really provided the foundation for classical physics, and it was really what brought physics to that next level. Why? because he was able to specify the laws of motion and express them in mathematical formulas. And him doing that, Pythagoras was sort of doing that before, but him doing that now in a scientific discipline, showing an understanding of the world through mathematics, was very, very powerful. Now, I know a lot of you guys are going, I came to psychology to escape mathematics. I know that's true, but you won't totally escape mathematics. So let's just kind of shift a little bit to psychology here. We sometimes, and this is a slide where I like to make fun of Albert Einstein. How cocky do you have to be to make fun of Albert Einstein, right? But, we look at Albert Einstein and we see this formula, E equals mc squared. And just in case anybody forgets, that's the energy that a certain thing has within it is a function of its mass and the speed of light squared. So the speed of light, c, is a constant. Okay, and so c squared is just a number. It looks nice as c squared, but he's basically saying the energy of an object is its mass times this certain number. What do I want to point out about that? Well, it's simple. That is a very simple formula. And if you can capture something in such a simple formula, that implies that its behavior is also very simple. Okay, so being able to capture things in mathematical formulas is cool as long as what you're capturing is a relatively simple thing. Then you can almost, like, maybe you only need to know about 2 or 3 things in combination to predict what it is what you're interested in. And if so, you can capture it in a formula. If I were going to do a psychology experiment, if I were going to put you in some situation and I was curious about how you were going to respond, I mean, maybe even that situation is, I don't know, I walk up to you in the hallway. We'd never do this, by the way, but I walk up into the hallway and I say, I don't know, I say something weird to you. I say, hey, why did you come to this university? Shouldn't you have gone to a different university? I don't know, I just picked that. How are you going to respond to that? If I want to predict in advance how you're going to respond to that, well, what do I need to know? Here's the problem with human behavior. It's so complex and so multi-determined. I would probably need to know, I don't know, what's going on in your life right now? Have you just broken up with somebody? Are you in a new relationship? Your social status may change how you react. How well did you sleep last night? Have you been eating well? Are you under a whole lot of stress these days? How's your relationship with your parents? I don't know. I could go on and on, right? We have all these things that impact us, and all of them can affect the way we behave and the way we interact. And so it's going to be very hard in psychology to ever be able to predict human behavior based on very simple formulas like we know from physics and chemistry and others. And that's what makes math tricky in psychology. Tricky, but let me introduce you to Ernest Weber. So Ernst basically started doing, well, he was born essentially, if we go back here, he was born essentially when Newton died, right? Newton died in 1727. This is 50 years past that before Weber was born. And it's going to go right up to right about the birth of psychology. Weber dies around the time psychology was born, you're going to see. So he was kind of between those two, between Newton and psychology. And in fact, his work is what helped make psychology be considered a viable discipline. How do I express this well? Well, Ernst Weber called himself a psychophysicist. So let's just jump right in here. He would ask people to do weird things. So I'm showing you 2 apples here in a person's hands, but let's imagine they're not apples. So first of all, let's imagine this person is blindfolded. They put their hands out like that. And what we do is we put a weight in each hand. And we're going to continually change the weights in the hands, but we put a pair of weights in this person's hands and we say, which one is heavier, the left or the right? And they try to figure it out. I think the left is heavier. I think the right is heavier. Maybe they say, I don't feel any difference at all. And so we do this with a bunch of different weights, okay? So sometimes this one's a lot heavier than the other one. Sometimes it's lighter, etc. So we keep trying this with a bunch of different things. Here's what Weber found. So I'm going to have to explain this graph to you a little bit. Background intensity. What he means by that is, okay, let's call one of these weights, I'm going to call it the baseline, and I'll call the other one the referent that we're going to compare to the baseline, okay? So the background intensity is how heavy that original baseline one is. So we put an original one in the person's hand, and now we put this other one. And what this is saying is how different in weight is that other one, okay? And what you see from his data is that if you're asking about something called a just noticeable difference, how different do these two have to be before a person can detect it, before they can say, I feel the difference, this one's heavier? Well, the answer to that question, how different do they have to be, depends on how heavy that original one was. Okay, if the original one was pretty light, then they don't need much of a change in order to detect that there's a difference in the weight. Okay, they can say, oh, this other one's heavier or this other one's lighter. But if that first one's quite heavy, now they need a really big difference in order to detect the change. So let me just give you concrete numbers here. Let's say the first one was a gram of weight, and now we're going to put something in the other hand. Well, it might be about, maybe we give it 1.01 grams, and they're like, that's the same. 1.02, that's the same. And maybe we get all the way to 1.1 grams, and then they go, oh, okay, they're different. I can feel it. This one's heavier. So it was a 10% change. We needed, the original one plus another 10%, 1.1, and that's when they could feel the difference. Cool. So what if we start with 10 grams now in the first hand, and we give a second weight? Can they tell the difference at 10.1? Because it only took 0.1 earlier. Well, no, they can't. What we need is 11 grams in the other one now. We need another 10%. Okay? So what Weber showed is there was a constant. In order for people to tell the difference, and I've been talking about weight, but it could be the brightness of two lights or the loudness of two sounds. In order for people to see a difference between two stimuli, there's a ratio that has to be held up in terms of that difference. And if that first thing is really loud or really bright or really heavy, you're going to need a bigger difference before you'll detect the difference than if that first thing is quiet or light, etc. Then you just need a little bit of difference. But the ratio stays the same. Okay, it's a constant. So this has become known as Weber's law, that the difference relative to the original that you need is a constant. And so this is what he called a difference threshold. So I is the original stimulus intensity. K signifies the proportion on the left side of the equation remains constant despite variations in the I. So as long as, if I goes up, then that change of I has to go up with it. Okay. The details of this aren't absolutely critical, except for this point. What Weber is showing, the weight is the objects out in the real world. Us being able to detect the difference, that happens in our mind, right? That happens in our brain. And so what Weber is showing is there's a mathematical relationship that defines how real world things affect our minds, how we see them, hear them, feel them. And because there's the math, he started to convince people we can start to understand the mental world with numbers, with math, which instantly gave psychology a hint of respectability, okay? And probably was one of the reasons why, countries were willing to put money into this fledgling discipline of psychology, because they started to think, hey, we can study our minds mathematically, scientifically, okay? Herman von Ebbinghaus kind of kicked this up another notch, okay? And Herman von Ebbinghaus is going to kind of span the birth of psychology. The birth of psychology would be the late 1800s, and so he's kind of across them. But he was also doing interesting experiments. So he created a bunch of what he called CVCs, consonant, vowel, consonant. So it could be things like JOS, GEQ. So he was trying to create stimuli that had no meaning. And what he wanted to study was memory. So he created a bunch of these. So let's say he had 12. And the first thing he did was say, I'm going to memorize these 12. And so he intentionally wanted these things that didn't have any meaning or didn't have any association. And so he would have to work and try to memorize what these 12 things were. And he kept track of how long it took him to memorize. And one of the things Herman did really well is he was very precise in his methods. And so he would even define memorize. How do I know when something's memorized? Well, it's when I can turn that list of 12 over and write them down once, and flip that and write them down twice. If I can retrieve all 12 accurately without looking twice in a row, then I got them. Okay? So then you'd say, okay, now I got them. Now what I'm going to do is let time pass. Waited some time. Different amounts of time. He did this experiment over and over, always on himself. So he waited different amounts of time at different times. And then he tried to recall them. And what he was interested in was forgetting. How am I going to lose these things as the passage of time? I could remember all 12 right after I studied them, but what if I wait a little bit of time? And he showed this, the now famous forgetting curve, as it's described. And he basically showed, hey, if I just wait 20 minutes, I can now only remember 58% of them. So I've lost a bunch of them already. In 1 hour, I've lost even more. In 9 hours, even more, etc. But you get this sort of nice, declining, exponential, nice mathematical function suggesting how we lose access to information in our minds. Math, mind. Another important sort of study that started to make people think, okay, maybe psychology can be scientific because you can use math and numbers, okay? These days, as I highlight here, it's still a kind of a funny thing in psychology. If I go over to the right here, most of you guys, especially the ones that say, oh, I took psychology because I didn't want to do math, and then you find out, what, I have to take a stats course? Yes, you have to take a stats course. So we use math as part of our scientific process and in order to find out what the results of an experiment mean. So we certainly use some math, and it's become an important part of the psychological scientific process. We also sometimes use math now in theory. So this gets back to me making fun of Einstein and me saying, that's a very simple equation that he's got there. And in psychology, everything is much, much more complex. So in psychology, we're never probably going to have that equation that describes human behavior in any way. But we're now creating things called artificial neural networks. We're creating models of the mind, models that are mathematical models, computational models. So in this model of the mind, it's all about the connection. These nodes are seen as neurons, and these links are seen as the connections between neurons. And what you can do is teach these models certain things. They can retrieve information. They can do all sorts of things humans can do. But ultimately, they're doing it in a mathematical, computational way, but in a much more complex manner than a formula. Formulas, I know, look intimidating, but at their core, they're simple. They're easy. They're usually linear. They're usually very straightforward kind of things. That's not going to work for psychology. But math continues to be an important thing. There's a subgroup of psychologists who are applying a lot of these mathematical principles in their work. Okay, so I just wanted to give you that because as we go through the chapter, this a power of mathematics to kind of influence people will come out every now and then, and I'll refer to it. So I just wanted to start with a short little lecture. This is what all the lectures are going to be. So a lecture on that. Okay, cool. Thank you very much. I will see you at the next lecture. Bye-bye.